you here? So I'd like to, before I start, get some idea of who you all are. So who would self-identify as a biologist? No biologists. That's cool. Who would self-identify as a physicist? Oh, an awful lot of you, okay. Material scientist? Okay, about the same number. Chemist? So that looks like a third, chemistry, material science, and physics. Okay, that gives me some idea of what to stress and what not to stress. I prefer to have people ask me questions during a talk, rather than stacking them up until the end. This is a terrible time to be giving a lecture straight after lunch. Keeping people awake is hard. And so one way of keeping people awake is for them to ask questions, or I can ask you questions. So, you can do it either way, but I prefer it if you ask me the questions. Okay, let's get started. Let me just say, well, wait a minute, I guess I have to turn this thing on. Let me just say that several of us have given these talks over the years, and we tend to trade view graphs backwards and forwards. So let me just acknowledge some of my friends who have provided view graphs for this. So let's start with X-rays. You all probably know that X-rays were discovered by Röntgen just before the beginning of the last century. And in fact, Röntgen observed that photographic plates fogged even though they were inside paper envelopes when they were put next to cathode ray tubes. He hesitated to make that public because he thought that if he was wrong, that there was some radiation that went through the paper of the envelope, that his reputation might be ruined. But he eventually did make it public. And what you see on the right-hand side of the view graph is the first ever medical X-ray taken of Röntgen's wife's hand. And she is reputed, when she saw it, to have said, "I have seen my death." And you can sort of imagine that if it's the first time you'd ever seen anything like this. You can see a couple of things from this. You can see that that X-rays are well transmitted through basically water, which is what your flesh on your hand is made of, that they are somewhat attenuated by calcium, which is the heaviest element in your bone, and that they are massively attenuated by gold. So you sort of already from this view graph get the idea that there's some dependence on atomic number of X-ray transmission through things. Synchrotron radiation, which is what you'll deal with when you go to Argonne National Lab and to the APS, which used to be called, which is the I get confused. It's the Advanced Photon Source. I know it as the American Palatial Synchrotron, which is what it was jokingly known as in the 80s. Synchrotron radiation is produced by electrons that accelerate in a direction perpendicular to their velocity. In other words, in principle, electrons that go around in circles inside an accelerator called a synchrotron. And the first observation was from this synchrotron that was built by General Electric in 1946. Here you can see a kind of a schematic of it. The electrons are going around in circles, and the synchrotron radiation, that's the X-rays, are coming out along the direction of travel of the electron perpendicular to the electron's acceleration, because the electron's acceleration, of course, is tangential as it goes around in a circle. You're used to the fact, those of you who have had physics courses are used to the fact that accelerating charges radiate electromagnetic radiation, and generally from an antenna they radiate essentially in all directions except the direction along which they're moving backwards and forwards. And so the pattern of emission of radiation is more or less isotropic, with that one exception. That's not the case for synchrotron radiation. It's emitted preferentially in the forward direction, and that's because of relativistic effects, because the electrons are traveling at speeds approaching the speed of light. So this emission diagram, a function of direction, gets distorted into this very forward cone of radiation, which has a very small divergence. It's like a laser beam. You know, the laser beam is has a very small divergence. The spot on the wall is almost the same size as the spot that's coming out of the end of the laser. And similarly with synchrotron radiation, it's very much directed into the forward direction. X-rays have been used very widely since they were invented, or discovered, excuse me. And there have been, I think, over the years, since the discovery of X-rays, 28 Nobel Prizes which are in some way related to X-rays. The most recent, I think, of those was in 2009 for studies of the structure of the function of the ribosome. Since we have no biologists here, that will be absolutely no interest to anybody, right? The ribosome is the organelle inside the unit cell, inside the cell of which translates DNA into protein, and these people got the Nobel Prize for discovering the structure of the ribosome. By structure, I mean where all the atoms sit. And based on where all the atoms sit, they were able to propose, or actually to demonstrate the veracity of models for how this organelle works in translating DNA into protein. So that's pretty important stuff. This area of protein, so-called protein crystallography, which is determining the structures of various proteins using X-ray diffraction, is a very important field. It's probably the biggest single type of experiment that is done at the APS now, and at all the synchrotron facilities for that matter, and is very important, for example, in what's called rational drug design. This is an example from the fact that ribosomes in bacteria and basically you have slightly different chemical structures with just one amine group difference, and that difference can be used to generate an antibiotic, the name of which I've forgotten. It's not in the slide, but it doesn't matter, that will bind to the ribosome of a bacteria and prevent it, or actually prevent it producing a complete protein from the bacterial DNA, and therefore interrupt its replication. So this type of X-ray protein crystallography has become extremely important, and you'll see examples of it as we go through, or as you go through the next couple of weeks. I just wanted to make the point that it's not only the structure of molecules that is related to their function, but also the way they move. And so there are various tools for looking at the way that molecules move around in solids or in liquids. And X-rays and neutrons are within that arsenal of tools that are used for exploring what we call the dynamics of molecules, that is to say, how they move. And we'll see more about those as we go through these lectures and other lectures later in the week. Paul mentioned Cliff Shull. Cliff Shull was a pioneer of neutron scattering. Here you can see some of the history of neutrons, sort of paralleling the history of X-rays that I showed you earlier. Neutrons were discovered after X-rays. They were discovered by Chadwick in 1932, and there have been nowhere near as many Nobel Prizes related to neutron scattering as there have to X-ray scattering. I think I can count 4 or 5, and eventually in 1994 Cliff Shull, who's an American, and Burt Brockhouse, who both of them are dead now, a Canadian, were given the Nobel Prize for work related to development of the technique of neutron scattering, which I'll show you on the next view graph. And so these are some of the sort of seminal events in neutron scattering history, and you can see Shull's name associated with several of them. You can see Wallen's name associated with several of them. If you go down the hill here, you'll see a building called the Shull-Wallen Center, which is a joint institute for neutron scientists. Wallen was not given the Nobel Prize. Nobel Prizes are not given posthumously, and Wallen was dead by the time the Nobel Prize was awarded. But he would undoubtedly have got it had he been alive. So neutrons, how are they produced? I told you how X-rays were produced. Neutrons are produced in two ways, as Paul Langen told you, both of which are available on this site. One is nuclear reactors. This is actually the nuclear reactor in Grenoble. Paul told you that the Haifa is the brightest source of neutrons in the world. If this auditorium was in France, the person standing up here would tell you that the Institut La Langevin has the brightest source of neutrons in the world. They're about the same. All right. Yeah, 1 or 2 neutrons. So this thing consists of a fuel element. Here's what it looks like from the top. It's a cylinder, stands about yay tall, is about 1.5 feet in diameter, and the fuel in the fuel element is in the. You can't really see them here, but they're plates of fuel separated by spaces. And the reason for the spaces between them is that you have to force water between these plates to cool them in order to prevent the reactor melting itself when the uranium fissions. This is Cherenkov radiation. It's a very pretty blue color. This is looking down into the pool of the reactor. Any of you know what that's caused by? Any of the physicists here? Yeah, that's exactly right. The electrons, charged particles that exceed to be precise, the phase velocity of light in the medium through which the dielectric medium they're going through. In this case, water. So this is a pool of light water in which cools as part of the cooling system of the reactor, and the charged particles going through that cause this beautiful blue glow, which you see in every nuclear reactor. The fission process is one in which, of course, uranium-235 nuclei fission into 2 nuclei which are roughly equal atomic weights. They're not exactly equal generally. And with each fission event, you get about 2.5 neutrons ejected on average. One of those neutrons goes on to cause fission in another uranium-235 nucleus, giving you a chain reaction. And the other 1 and a bit neutrons are available to leak out of the reactor and to be used for neutron scattering. So that's how we get the neutrons for neutron scattering. One of the issues with nuclear reactors is that this process gives out a lot of energy, 200 mega electron volts per fission, roughly. That has to be cooled, water is used for that cooling. And the ultimate flux of neutrons that you can get out of a fission reaction is limited by that cooling. You want to make the core of the reactor as compact as possible so that you get as many fissions happening as possible in a particular region, and you've got to get the heat out. And just as in your home bathroom, it's the plumbing that always breaks down, right? Water tends to leak, and so that's the sort of technical issue. The other process is called spallation. Paul told you accelerate effectively protons and bang them into heavy metal targets. In this case, here it's mercury. Other places use tungsten or tantalum. In this case, that proton causes the heavy metal nucleus to go into some sort of excited state and evaporate off lots of different types of particles, pions, neutrons, you name it, lots of different stuff. And in fact, for every every proton that hits a mercury nucleus at this facility, so every 1 GeV proton, you get 24 or 25 neutrons out. So in some sense, it's a neutron amplifier. You put in 1 proton, you get 24, 25 neutrons out. Also, the amount of heat that you leave behind per neutron is about 1/10 of what is left behind with fission. So it's easier to cool. You don't have as much heat to get out. So Paul told you that HIFA was 85 megawatts. The spallation neutron source is 1 megawatt, right? So you'll see lower power numbers associated with spallation neutron sources. In addition, as Paul said, the beam is pulsed. That means you're not producing heat all of the time. You're producing the heat only when you have a pulse. So this is, I thought you'd get plenty of pictures of Argonne National Lab and Oak Ridge National Lab, so I decided to be different. This is Grenoble in France. This is the European Synchrotron Radiation Facility, the European equivalent of the APS, and this is the ILL reactor on the same site. That's a similar reactor to the HIFA reactor here. Talking again a bit more about neutron scattering, one of the first things that Charles and Wallen did was to show that the antiferromagnetic structure proposed by Néel was correct in manganese oxide. It's one of the earliest successes of neutron scattering. And the point I wanted to make on this slide is that most of these problems don't just get solved and they're done. So Charles and Wallen showed that the magnetic moments of the manganese atoms in manganese oxide were up, down, up, down, up, down, right? But that wasn't the end of the game. They then showed that late in '51 that the magnetic moments were ordered, had ferromagnetic order in 111 planes, and that 111 planes were antiferromagnetically ordered from one to the other. Then, even as late as 1988, there was more information that came in about how the magnetic moments were arranged. And then even in 2006, that there were slight out-of-plane components of the magnetization. So even when you think the problem's solved, as the equipment improves, you find that there are new wrinkles that come out of what seem to be old problems. So and that's one of the reasons, of course, that we're always trying to improve the number of neutrons or the number of X-rays that come out of these sources, and because it leads to new science. And you'll see a little bit about that as we go on. So these were the two guys who got the Nobel Prize for neutrons, Cliff Shull, seen here with an early diffractometer, and Bert Brockhaus. They were given the Nobel Prize for, as the Swedish Academy of Sciences said, inventing a technique that showed where the atoms are and what the atoms do or how they move. I think Brian told the lecturers not to show this slide because Roger would show it once and we didn't want to see it in every damn lecture, right? Okay, so this is the one time you may see this, hopefully. So this is an extract from the Swedish Royal Academy's poster, and they show here what is really an archetypical neutron scattering experiment. Neutrons from a source Now, the fact that the source of neutrons is labeled a nuclear reactor but actually looks like a washing machine has more to do with the politics of nuclear power in Sweden than with how neutron scattering works. We do not get neutrons from washing machines. The beam of neutrons then comes out to a crystal, which sorts out the neutrons according to their energy and sends neutrons of a particular energy towards a sample, which is crystalline in this case, and then the neutrons are scattered by the crystal into various directions and detected. And that's all there is to any neutron scattering experiment, really. I mean, say it again. That's a good question. I hope I'll get to that, but just to as a quick statement, the energy so there's something called Bragg's law, which specifies the relationship between the wavelength of a neutron that is scattered by a crystal and the angle through which it's scattered. And we'll get to that in maybe the next hour, I think. And so by setting up this crystal at a particular angle with respect to the beam, you only get neutrons of a particular wavelength off it. And we'll come back to that. But thanks for the question. And so this is an archetypical experiment of a type called an elastic scattering experiment or a diffraction experiment. This thing is slightly different. You'll see that there's this crystal that sorts the energies of the ingoing neutrons, just like there was up here. But there's also another crystal after the scattering from the sample, which sorts out the energies of the neutrons that are scattered by the sample. So in this case, you know both the energy of the incident neutron and the energy of the scattered neutron, so you can see how much energy has changed. In this first case, the diffraction, you can't tell how much the energy has changed. So these turn out to be two different ways of doing neutron and X-ray scattering, in one of which you determine the structure, and in the other one of which you determine something about the motion of the atoms in the structure, because you know the change in energy of the radiation when it's scattered. I'm not, let me do this one, but I'm going to skip a bunch of view graphs in a minute because we'll get behind if I don't. So neutrons have a number of advantages which they have in common with, some of which they have in common with X-rays, and I'll try to emphasize that point. So one of the advantages of neutrons for looking at structures is that they have wavelengths that are comparable with the distances between atoms in a solid. If you have a radiation of if you want to observe something of a given size, it's no good trying to observe that thing with a radiation that has a wavelength that's much bigger than that size. Because as far as the radiation is concerned, the object looks like a point if its size is much smaller than the wavelength. If it looks like a point, it will scatter isotropically and you can't tell any details about it. So in order to be able to see detail about something by scattering radiation from it, including the detail you can see of me when you look at light scattered from me, you have to have radiation whose wavelength is smaller in general than the size of the object or the detail you're trying to see. So that's an advantage for neutrons. It's shared with X-rays. Neutrons and X-rays all have, as you'll see in a minute, wavelengths that are measured in angstroms or in tenths of nanometers. An angstrom is a tenth of a nanometer. I'm old, so I speak in angstroms. The modern world speaks in nanometers, which is a unit which is 10 times smaller. If you want to measure the change in energy of a particle that is scattered, and that change in energy is caused by energy that is either given up to the sample or that the sample gives to the incident radiation, then it's a good idea to have the energy of the incident quanta roughly in the same ballpark as the energy of the excitation that you're scattering from. Why is that? Well, if you come in with 10 units of energy and you leave behind 5, then you've got 5 to measure, probably reasonably easy since you knew how to produce 10 in the beginning. But if you come in with 10,000 units of energy and you have 5 units of energy change, that's a very small fractional change in the energy and can be very hard to measure. So that's an advantage that neutrons have that X-rays don't. X-rays, as you'll see in a minute, have much higher energies than neutrons for the same wavelength of the radiation. Neutrons are very penetrating. That means that they go through sample containers. You can have sample containers that are made of quite thick steel, for example, and get neutrons through them. The fact that neutrons are penetrating means they interact weakly with materials. That's a double-edged sword. Interacting weakly with materials means that the scattering is weak, right? In other words, you send in a beam of 100 particles, you may only get one scattered because the beam interacts very weakly with the sample. But it's an advantage as you'll see in a minute, in describing the scattering, because you don't have to, for example, think about multiple scattering, right? If the probability of scattering is so small, then the probability of multiple scattering is much smaller, so you don't have to try to sort all that out, which you would if you were doing electron scattering, for example. So that's a two-edged sword. For X-rays, the X-rays are not as penetrating, as you'll see in a minute, and that can be a disadvantage. This is very important, especially in biology, but also in chemistry. The fact that neutrons tend to be scattered differently by different isotopes. So you can, by isotopically enriching a sample in certain ways, in biology that's often replacing H2O by D2O, because it turns out that hydrogen and deuterium scatter differently. You can highlight various parts of a molecule that you're interested in. And then finally, neutrons are scattered by, neutrons have a spin and hence a magnetic moment. In other words, you can think of them as little bar magnets that are flying through the air. And little bar magnets tend to interact with magnetic fields. And so they're scattered by magnetic fields. So I think I've said these, or I said this one, the fact that the signals are weak is a disadvantage, of course, because signals are weak compared to backgrounds. Some elements absorb neutrons strongly, so you can't use them generally for neutron scattering. There are exceptions, though. And then we'll come to this one. This is a technical restriction, but it's a very important one. Okay, so I'm not going to go through all of these historic accomplishments. I'm going to skip over them. You've got them in the view graphs if you want to have them. But if I go through those, we'll never get anywhere. So essentially, the bottom line of all of this is that both neutrons and X-rays allow you to understand how constituents of matter are put together, right? How they self-organize into assemblies. I mean, even a crystal, for example, that is grown out of a liquid or a solution is a self-assembled object with a structure, right? A crystalline structure in that case. But in the case of nanoscience or structures of interest in nanoscience and technology, the structures are much different often than long-range crystalline order. So determining how those structures, what the structures are when they're put together, when they self-organize, is the role that neutrons and X-rays have in the study of materials. And then, having determined what this structure and dynamics are, figuring out how that leads to and is related to the way the materials behave is a really important thing. So if you're interested in materials, you've got to be able to synthesize it, you've got to be able to characterize it, you've got to know its structure, and then you can figure out why it does what it does in the particular situation that you're interested in a technology, for example. And then how emergent and collective properties arise. By which I mean, if you had hydrogen, oxygen, carbon, sulfur, and nitrogen, and you know about those 4 elements, understanding how a ribosome works would not be something you would figure out in a day or 2. Right? It's an emergent property which is dependent on the exact way in which all of these things go together and how they function in how the function develops in a hierarchical way as the things are put together. So where are we, Brian, on quarter off? Okay. I should be able to stay awake till then. How about you guys? Are you staying awake? All right. Anybody have questions? Not yet? Okay. All obvious, right? How many of you done X-ray experiments, by the way? Almost all of you. Okay, good. So you all know this stuff. How many of you done neutron experiments? Almost the same number. Okay, so you know this stuff. Then I am surprised you're staying awake. Okay. All right. So here's how the difference is between neutrons and X-rays interacting with materials. Neutrons have effectively 2 ways of interacting with materials. One is by interacting with the nuclei, and the other is by, because they have a magnetic moment, interacting with magnetic fields inside the material. The thing to remember about that, by the way, is that neutrons see B, not H. That's a really important distinction. That was a source of great frustration in the early careers of people like Richard Feynman and Schwinger, and was eventually resolved. But neutrons do see B. So if you want to figure out how they're scattered, it's the B field you have to worry about, not the H field. X-rays are scattered electromagnetically. That is to say, they have an electric field associated with their electromagnetic field, and it's principally that electric field accelerating electrons that cause the scattering, and we'll talk about that. Here's a plot of the penetration depths for various elements for neutrons and X-rays. For X-rays, you can see, so this is the penetration depth in meters on a logarithmic scale. So this is a centimeter, this is 1/10 of a millimeter. And you can see that in general terms, the X-rays have this 1/z². This is plot against atomic number, so they have this 1/z² dependence with some peaks at strategic positions here. Whereas neutrons, effectively, there's no organized structure to it. It's just all over the place. It's not, of course, random, but you can't tell. If I tell you that I've got an atom of this atomic number, you would be hard-pressed to tell me what the penetration depth is. You would have to go off and do an extremely complex nuclear physics calculation that people now know roughly how to do, but they would never pretend to be able to predict these numbers with any accuracy. You can see there's some outliers. Cadmium down here, boron down here. Those, of course, then become materials that you want to use for shielding for neutrons, because, as you can see, the penetration depth is so much smaller. You can see, for example, that lead up here really is good for attenuating X-rays. And so those of you who have X-ray sets in your university lab basement have, I can see Dylan smiling, have mostly lead around their X-ray equipment except for holes, right? And where there's lead, they're well shielded, and where there isn't lead, they're not. Lead is useless for shielding neutrons. It's not a shielding material for neutrons. So here are the sort of types of interactions that one has of the different materials. In the case of neutrons, one type of interaction is absorption in things like cadmium and boron. In that case, the probability of absorption goes essentially as 1 over the velocity of the particle. So the faster the particle, the less absorbed it is. And then there are two different types of scattering that we'll get into in a few view graphs. One is called coherent. What that means is that the way the neutrons that are scattered from different nuclei have some well-defined phase relationship when they're scattered from two nuclei at specific positions. So if I scatter a neutron from this position and from this position, there's a well-defined phase relationship between those. So they can add, and you can get interference patterns, just like you do with other types of radiation that you're all familiar with from undergraduate classes, right? The Young slit experiment, for example, something like that. And then there's incoherent scattering, where the scattering does not depend upon where the nuclei are. There's no information about the separation of the nuclei contained in incoherent scattering. It just goes everywhere, scattered uniformly into 4 pi radians. There's no structural information available from that scattering. There is some dynamical information available from it, as we may see later. Again, there's this magnetic interaction between the dipole moment of the neutron and the B field inside the material. The B field can come from a couple of different places. The main place it comes from is from unpaired electrons. Right? When you have paired electrons inside atoms, their spin moment, the magnetic moments cancel each other, so you need unpaired electrons in order to produce magnetic fields inside materials in general. X-ray is very similar. There is an absorption. There are absorption effects. The X-ray kicks an electron from one orbital into another in the atom, and it may then eventually the electron may redescend back into its ground state with the emission of a fluorescent X-ray, and this is a process which goes as 1 over the energy cubed of the X-ray. Obviously, there's no structural information in this, just like there's no structural information available when a neutron is absorbed by a nucleus. The neutron is gone, the X-ray is gone in this case. Then there are two types of scattering that we'll talk about in a minute of X-rays. Thomson scattering, which is elastic. In other words, the energy or frequency of the X-ray photon that comes out is the same as the energy or frequency of the X-ray photon that was incident. And that type of scattering is coherent in the same sense as I described about coherence up here. That is to say, there is a well-defined phase relationship between X-rays scattered between objects that are separated by some distance. And then there's Compton scattering, which is the case where the X-ray, you probably remember this from your undergraduate physics, where the X-ray comes out with a different wavelength than it went in with, so it's an inelastic process. This comes back to the point that I made earlier. Don't want to belabor it, but basically, in order to see things with radiation, you have to have a wavelength which is comparable in size or smaller than the object that you want to see. And this is for X-rays, this is the relationship. And in a sense, I think I put this view graph in here because it was one that had this relationship. It tells you the relationship between the energy of an X-ray and its wavelength. An X-ray that you might use at a synchrotron source might be 30 keV, for example. So a 30 keV X-ray will have a wavelength of 1/3 of an angstrom, or about 0.03 nanometers. And the separation of atoms in a crystal will be a few angstroms. So you can see that you're now into a range where you expect to be able to see details of interatomic distances, because your wavelength of the radiation that you're using is smaller than the distances you're trying to look at. This is just another way of saying the same thing, so is this. This is a comparison of various techniques that are used to study structure. This is the length scale of the structure across the top here in nanometers. Here's a nanometer. Here's something much larger than a nanometer, still sub-millimeter. And you can see that at this scale, you can actually measure things by radiography, same way as the dentist looks at your teeth with X-rays, right? I mean, in other words, you get a picture of your tooth in an X-ray beam, and so you can do that both with X-rays and with neutrons. You can image things. All of the stuff that's smaller than that, you have to study by various scattering techniques that give you pictures in reciprocal space. We'll get to that in a minute for those of you who are not comfortable, don't live in reciprocal space. And that's in some sense a disadvantage, as you'll find if you write papers about neutron and X-ray scattering, right? Because your colleagues who are not familiar with scattering want to see pictures, just like you would in any other context, right? You'd rather see a picture than a bunch of points on a graph and then have to interpret them. So there is a disadvantage to that in some sense. But anyway, these are the various techniques that can be used. And at every stage in the development of these techniques, that you go through stages in which there's an argument as to, why would we want to do this anymore because this other technique has taken over. You'll hear this with neutrons and X-rays. Well, X-rays are so bright. Why do we need neutrons? Well, the answer is that they're scattered differently. And because they're scattered differently, you get different types of information, even though it's the same length scale. So don't be fooled just because these things overlap in length scale into thinking that you don't need all of them. You do, because they give different, because the interaction mechanism with the material is different, so you get different types of information. This is the same sort of graph, but now looking at both the length scale and the time scale of the structure inside the material. So here once again across the top is the length scale that you're measuring, 1 nanometer here, 100 nanometers here, and at the bottom is this reciprocal space scale, usually denoted by Q, the momentum transfer. We'll get to that in a minute. So basically, let's concentrate on this as the length scale, and over here on the time scale of the motion. And here this is 1 picosecond. So this is slower motions down here, slower going down in this direction, faster going up in this direction. And you can see this is actually a fairly old view graph. It's probably at least 5 years old, probably more. And at the time that it was made, these arrows indicated the directions in which the various techniques were expanding. And I bet you that that somebody who is a practitioner of inelastic X-ray scattering would tell you that box is bigger than I've drawn it here. What you'll see is that there's a fairly large range for neutron scattering and overlapping range for inelastic X-ray scattering and X-ray photon correlation spectroscopy. So again, what's happening as these facilities are developing is that the whole space of distance and time scales is being covered increasingly by more and more different techniques. So let's, I want to, probably next lecture I want to talk about scattering cross-sections, but let me introduce them a bit in the last 5 minutes here. So a neutron, of course, is like any quantum particle. It has both wave and particle-like properties, as de Broglie taught us. Namely, if you know its wavelength, its momentum, you can determine its wavelength from the de Broglie relationship, that the wavelength is just Planck's constant divided by the momentum. The neutron has a mass. It's about the same mass as a proton, not very different. It has no charge. It has a spin 1/2. It's a fermion, so it has the same spin as a proton. That, incidentally, is why we can't produce neutron lasers, and why we never will, which is kind of a disadvantage. It has a magnetic moment. The fact that that magnetic moment has a negative sign is a manifestation of the fact that the magnetic moment is oppositely directed to its spin. Generally, that's not a particularly important thing to remember, but if you see it with a negative sign, just remember that that's the case. Of course, it has a velocity. It has a kinetic energy, which is just 1/2 mv squared. It has a wave vector. What's a wave vector? A wave vector is a vector which is equal in magnitude to 2 pi divided by the wavelength, and has a direction along the direction of travel of the neutron. So this is a vector, which is equal in, as I said, in length to 2 pi over lambda. And you'll see that that's an important number in all of the neutron scattering and X-ray scattering experiments that we do. You can associate a temperature with it just by saying that the energy, the kinetic energy, is equal to Boltzmann's constant times the temperature. So, and it's good to get. And that, in a sense, is how neutrons are classified. You'll see over here that neutrons are classified according to whether they're cold, thermal, or hot. The neutrons that we use for scattering don't come directly from the uranium fissions in a reactor. Those neutrons are very energetic. They have energies which are typically kilo or mega electron volts. They're useless for neutron scattering purposes because their wavelengths are way too short, and they're basically hardly scattered either. I'm hoping you have some more batteries for this thing, by the way. Do you think we can find those? Yeah, okay. So cold neutrons have energies in the sub-10 milli-electron volt range. You'll see in a minute that, or you will have seen on that view graph a little earlier, that typical X-rays are kilo electron volts, right? So 1,000 electron volts. This is 1,000th of an electron volt. So typical neutron energies are very much less than typical photon energies in the X-ray region. Their temperature equivalent is between 1 and 100 Kelvin. To produce them, that means you've got to take the neutrons that come out of a reactor and cool them down somehow. And you do that by putting, in general, a bottle of something cold next to the reactor core. And often that something is hydrogen or deuterium or something like that. And the neutrons rattle around inside that material, which is called a moderator. And eventually they come into equilibrium with the material in the moderator. And so their typical energies are the same as typical energies of molecules in the moderator. And so they would, if the material is cold, they would be described as cold neutrons. They would have a low energy. The wavelengths here are typically 4 angstroms to 30 angstroms. Let's see, what are they? Yeah, that's right. And so you can see how these things vary. Here are some useful conversion equations. If you know the velocity of the neutron, you can find out its wavelength. So, for example, a 4 angstrom neutron has a speed of 1,000 meters a second, pretty much. Good number to remember. Ultra cold neutron has a speed which some of you could outrun, 8 meters a second, right? I couldn't, but some of you could. So that sort of sets the range of them. And here's a translation from energy into wave vector. And Brian is sitting on the edge of his chair, so I'm thinking that he wants me to quit and then start again, right? So, okay, so let's do that. And so think about the questions you want to ask and ask them at the beginning of the next session, which starts at? In 15 minutes. See you later. Neutron scattering experiments know among neutron scatterers there is an error on any count of root n. So what Brian is telling you is 20 plus or minus 4, is that what you're telling him? All right. So this is the same sort of thing as I was just telling you for neutrons, but about X-rays. Again, wave and particle-like properties. And here is the correspondence between wavelength and energy in this case. And if you remember back to this, a wavelength of about 1.5 angstroms was in this range of thermal energies, millielectron volts, whereas in this case, a wavelength of 1.5 angstroms is equivalent to 8 kiloelectron volts for X-rays. So there are lots of places you can do this sort of stuff. This is a map that was correct probably 10 years ago. Since that time, various places have shut down. The IPNS was a neutron scattering center at Argonne. That shut down. In its infinite wisdom, the Department of Energy shut the one at Los Alamos down, leaving only the Oak Ridge site and NIST as neutron scattering centers in this country. In Europe, the reactor center in Berlin will soon shut down, as will the one in Paris, but there is a new source being built in Lund in Sweden, the European spallation source. So that, but anyway, there are plenty of places where you can do these things, especially synchrotron X-ray work. There are quite a few of those. Again, coming back to this comparison of X-rays and neutrons, there are many differences. There are these differences in the relationship between the energy and the wavelength, as I pointed out to you. But there's also a huge difference in the terms of the actual number of quanta that you can produce in sources. So let's just look at this number over here, which is the flux. That's the number of quanta crossing an area, in this case, of a square meter per second. Usually, incidentally, you'll see these numbers quoted as per square centimeter. So the canonical number here will be 10 to the 15. Not 10 to the 11. I can put it into MKS units here. So this is the ILL, or Haifa, same difference. Number of neutrons produced per square meter per second. Now look at the number of X-ray quanta produced by an undulator at the APS. It's 13 orders of magnitude bigger, and this view graph is old. So that number, this number has not changed, that one has gone up. So there is a huge difference in the brightness, in the flux. Okay, so that brings me to the point that what the words are. Flux is the number of quanta per square centimeter or per unit area per second. Brightness is the flux divided by the divergence, that is to say, divided by the solid angle into which you put the radiation. So this here is the divergence of a typical neutron beam, 10 milliradians by 10 milliradians. So the brightness is obtained by dividing this number by the divergence, and you get this number. Because this is a divergence in two different planes. Let's see. Yeah, 10 to the 4th, that's right. The divergence of a typical undulator beam is way less, right? Factor of 100 down here, factor of 1,000 down here. So you get the shear flux is up by 13 orders of magnitude, but the brightness, that is to say the flux per unit divergence, is up by even more orders of magnitude. Then you go to something called brilliance, which is the brightness divided by the energy bandwidth into which you're putting that radiation. And the energy bandwidth is given here. Typically, for most neutron scattering experiments, the energy, the level of monochromatization, the level to which the radiation has the same wavelength, is 1 or 2%. Whereas, again, down here for an undulator, it's 1/100 of a percent. So the brilliance has another factor of, 100 in it. So X-ray sources are much brighter, much more brilliant, and so you have to ask yourself, natural question, why would you use neutrons if you can use X-rays? The answer comes down, as I said before, to the way in which things are scattered. It doesn't matter how bright the source is if you can't get any information out of it, and we'll come to that as we go through. So this is the way the synchrotron radiation folks like to present. This is the world according to them, right? This was Röntgen down here, and now we're just rocketing upwards, and the future is enormously bright. There are some disadvantages to that. If you talk to synchrotron radiation people, they'll talk about diffract and forget. Right? They'll blast a sample with one pulse of X-rays, knowing that the sample is going to disappear someplace, and hoping like hell they're going to get a diffraction pattern out of it before it's blown away. So there are some, yes?
How does the new generation of light sources free electron lasers compare to this?
Somewhere up in the roof here? Yeah, I mean, and also because the radiation is coherent. The radiation that you get out of a synchrotron is coherent, but coherent over a certain width of the beam, right? Maybe 5-10 microns, whereas the coherence length for an FEL is much greater. And as one of my friends, who is actually the director of the FEL in Germany, said, and I think he's right, in the last century we looked at coherent structures, meaning crystals, with incoherent radiation, meaning synchrotron radiation. In this century, we ought to be looking at incoherent structures, that is to say disordered structures, with coherent radiation, which is FELs. So there's, but of course, at the moment with FELs, you get one shot a fortnight or something, and I mean, the number of experiments is limited. So you can't do everything with FELs, but it's obviously an incredible technique, and will teach us things that we could never learn with our current sources. This is the equivalent diagram to that for neutrons. It's also on a log scale, and you can see the effect of something that I talked about earlier. This is Chadwick. He discovered one neutron. This is, or of order 1, right? This is CP1 and CP2, which are a controlled pile, 1 and 2, which were at Argonne National Lab. And here you can see all the other reactors. They're basically flattened out. Here is HIFA, here's the ILL. HIFA is much bigger than the ILL, as you can tell, or the other way around, depending on where you are. But basically, the answer is they're the same. And they're the same because of plumbing, right? You've got to get the heat out. And there's just a limit to the heat you can get out. So reactors are basically flattened off. This is flux. Again, this is now in per centimeter squared, so the canonical number is 10 to the 15. There's another curve on here, which is this curve, which is for spallation neutron sources. This is an effective flux curve. What do I mean by that? Paul told you already that these spallation sources are often pulsed. So you do experiments differently. At a reactor, you monochromatize the neutrons. This gentleman asked, what's the point of the crystal in sorting the energies? Well, at a reactor, you have to figure out what energy neutrons you're putting onto a crystal, so you have to throw all the rest of the neutrons away. With a time-of-flight source, which you have pulsed, you can measure the velocity of a neutron just by how long it takes to get from the source to the detector. So you can use all the wavelengths because they're separated in time by the time they get to your detector. So comparing a pulse source and a reactor source, which is continuous, was one of the great ideological debates of the 1980s and 1990s. And it's a bit like, Catholicism and Protestantism and every other religion you've ever heard of. People get into, I was part of it, you get into these vicious arguments about, well, mine is bigger than yours, right? And it's sort of ridiculous looking back on it. But anyway, this is sort of what the community basically thinks is sort of a reasonable way to interpret the effective flux of pulse sources. And you can see SNS is up here, ESS is a bit higher, but this curve is not rocketing up in anywhere near the same way as the synchrotron curve. So it's probably not the right metric. So we've talked about a lot of these things. I think I've talked about all of these, actually. I don't think there's any that I haven't talked about. There's kinematic restrictions we'll come back to because it turns out to be important. But I think I've talked about all those. Similarly for X-rays, strong absorption at low energies, contrast issues. Somebody, I think, asked about this business of, well, here's an example. High TC materials were discovered in 1987. And even though every university has an X-ray kit in its basement, and everybody wanted to know what the structure of YBCO was, the first structure was found by neutrons, right? It was found by neutrons because, there's yttrium, there's barium, there's copper. Those all are heavy elements, and figuring out which was scattering and what the structure was. It was also an issue of twinning of the crystals, but let's not worry about that. But nevertheless, what it does show you is even when you think the answer should have been obtained by the brightest source, it wasn't, even though lots of people were trying to do it. So this contrast issue can be important. Radiation damage to samples. I mean, the ultimate radiation damage is it blows your sample away. So there are advantages and disadvantages of both, is the bottom line message. Okay, so let's start and get into some of the sort of gentle theoretical background. I promise you I won't try to dazzle you with too many equations. I hate it when people do that, when I'm sitting in the audience and try and talk me through equations, so I try not to do it with you. So you have the archetypical scattering experiment is very simple. You take a beam of some radiation, X-rays or neutrons, which is described by a wave vector. That is to say, it has a particular wavelength, lambda. Throughout these view graphs and in most of the books you'll see, lambda is always the wavelength. And you associate with that beam of particles, or quanta, a wave vector, which is just a vector whose length is equal to 2 pi divided by the wavelength, and whose direction is the same as the average velocity vector of the beam. You stick a sample in the beam, and you stick a detector over here, and you look at what neutrons are scattered with this wave vector. Now, incident wave vector I sometimes will call k naught, and sometimes I will call it ki for k incident. I'm not trying to confuse you. It's just that I produce the view graphs at different times, and I'm too lazy to change them. And you'll see both these nomenclatures anyway in different forums. The final wave vector, sometimes I'll call k primed, sometimes I'll call it k final. It shouldn't confuse you too much. So there is this wave vector incident, wave vector scattered. You can draw a triangle, and this wave vector, of course, is the wave vector transfer from the incident to the final wave vector. Think of it, if you like, as momentum transfer. This is just conservation of momentum. Momentum equals h bar k. So this is just a triangle which which expresses conservation of momentum. This Q here is called the wave vector transfer. It's usually denoted capital Q, sometimes little q. It shouldn't be too confusing. Sometimes there is a difference between big Q and little q. In crystals, one is often called the reduced wave vector, bringing the wave vector into the first Brillouin zone. But in general, it shouldn't be too confusing. So that's all there is to it. What did I mean in these previous view graphs when I talked about kinematic restrictions? Well, imagine you come in with some wave vector k naught, which corresponds to some energy of, let's say, a neutron. And let's suppose that energy is 10 millivolts. And let's suppose you have an 8 millivolt excitation in your crystal. So you're going to transfer 8 millivolts to the crystal. So you're going to come out with 2 millivolts, which means that this wave vector here is really short. That means there's a limit of the Q vector that can join these two. So you can't scatter from all phonons with that energy. You can only scatter from a limited set of particular wave vectors, and that's a kinematic restriction. It doesn't apply to X-rays because you come in with some energy like 30 keV. Your energy change is a few milli-electron volts, and so you can always make the triangle. So for neutrons, you have these kinematic restrictions. They're, in general, not that important, but for example, people wanted to know what the phonons and the lattice excitations in plutonium look like. It's pretty much impossible to measure those with neutrons. You can't get a big enough plutonium crystal, and even if you could, nobody'd let you measure it. So the first measurements were done by inelastic X-ray scattering at the ESRF with plutonium from Lawrence Livermore lab, tiny little plutonium crystal. And the reason it was easier was because of this lack of kinematic restrictions. So let's get into the definition of these things called scattering cross-sections, because that's what you need in order to be able to interpret any neutron or X-ray scattering experiment. So here's a diagram of your canonical scattering experiment. Incident beam through here, target, which is supposed to be at the center of a globe, and a sphere, and then the radiation is scattered in this direction into some little unit of solid angle here through a unit, an area denoted ds, and of course this is a little element of solid angle is just this area divided by the radius squared. Okay, so the definition of this thing called the total scattering cross-section, let's start with this. So this quantity phi here is the now you can read X-rays or neutrons for this, right? Doesn't matter, either one is it's the same. So phi is just the number of incident neutrons per second per unit area on your sample. Then this quantity called the scattering cross-section is the total number of neutrons scattered into this little total number of neutrons scattered into the whole sphere, every direction, divided by the incident flux. So that's a definition of the total cross-section. This thing here is called the differential cross-section, and it is defined, it's always written this way, d sigma d omega, and it's defined as the number of neutrons scattered per second into this solid angle, again divided by the flux, but also divided by the solid angle. And then finally, there's this thing called the double differential cross-section, which has the same definition as you might guess from this one here. Total number of neutrons scattered per second into this solid angle, into a little band of energy. So what does that mean? It means that it's the neutrons scattered between E and E plus delta E, right? So this thing here is a function of E, and then The band into which the neutrons are scattered, the energy band, is this. And then you divide by these three. You can, of course, define this thing for anything. I could define this for a complete sample, right? I mean, I can talk about the number of neutrons incident per square centimeter on my complete sample, but I can also talk about it in terms of a single nucleus, right? So, and if you talk about it in terms of a single nucleus, this so-called cross-section, which you can think of, if you like, as the effective area that the nucleus presents to the neutron as it's coming in, as a effective area for hitting, if you like, a target. All of these cartoons, incidentally, were drawn by a friend who had no knowledge of any science. He was actually a commercial artist, and I tried to explain to him what we were doing, and he invented these cartoons. So occasionally you see some of these cartoons throughout this talk. So it's a sort of area, it's the area that the nucleus presents to the incoming neutron or X-ray. Yes? That's a good question. So what you'll see as we go further is that this is the one you use if you want to just get structural information. That is to say, where are the atoms arranged in a crystal? If you want to get dynamical information, that is to say, how do the atoms move, then you have to know something about the energy that's transferred. So then this will be the cross-section that you'll want to measure. You remember that slide I showed you of the Swedish Royal Academy's poster? In one of them, there was, you didn't measure the energy of the scatter beam. That was measuring this. And then in the other one, you had this crystal after the scattering that was sorting the energies of the final neutron. That one was measuring, that one was measuring this thing. So in fact, Cliff Schall got the prize for this, and Bert Brockhaus got it for this. Yes? Yes. So this is inelastic scattering. This strictly, when you measure it, you don't measure only elastic scattering with neutrons. With X-rays, you tend to, because there's very little difference in the outgoing and the ingoing wave vectors. Elastic scattering, the two would be exactly equal. But with most neutron equipment, you integrate over the final energy of the exit beam. That's okay if most of the biggest signal is elastic, right? So-called Bragg scattering. And I'll try and remember to remind me to comment on that a little bit as I go along, if you remember. Okay? Yeah.
So the definition for sigma is the total number of neutrons into the whole sphere
Correct.
divided by the incoming flux.
Mm-hmm.
How is that? Is that number always 1? Because of whatever comes
No. In other words, what sigma will give you is the probability of scattering, and it won't be 1. That's right. So so if you hydrogen is a very strong incoherent scatterer. But even so, if you have hydrogen, then there'll be lots of neutrons that don't get scattered, and those aren't counted in that definition. So some of the neutrons don't get scattered. Other questions? And I've forgotten, of course, completely to say what the question was. All right, well, whatever. Okay. So the scattering cross-section is measured in a unit called a barn, which is 10 to the minus 24 square centimeters. Do not please ask me why it's called a barn. I don't know. And the attenuation of a beam going through something is just given by this exponential factor here, where you have the cross-section multiplied by the number of nuclei per unit volume times the thickness. And you can see that this is a 1 over length cubed. This is length squared. Note the definition, right? this is total number of neutrons per square centimeter, total number of neutrons per second, and this is neutrons per square centimeter per second. So this has a dimension of length squared. So the cross section has dimensions of length squared. So this is 1 over length cubed times length squared times length. So we've got it right. It's just a number. All right. So now we have to figure out. Let's do the next simplest thing, and let's think about holding a nucleus at the origin of our coordinate system and having a neutron come in and hit it and be scattered. Well, this is a monochromatic neutron, has one wavelength. If it has a wavelength, it means it behaves as a wave, and it's a wave which is e to the I k, that's its wave vector, times x, that's the direction it's traveling in. That's a plane wave, right? It has the same phase for everywhere in y. So you're thinking about a plane wave coming in that represents the neutron, and it's scattering from a nucleus. Now the nucleus is a femtometer in scale, 10 to the minus 15 meters. And the wavelength of the neutron is an angstrom, 10 to the minus 8 centimeters, 10 to the minus 10 meters, right? As far as the neutron is concerned, the nucleus is a point. It's 10 to the 5 times smaller than its wavelength. So if you scatter from something that's a point, you scatter isotropically. There isn't any information in the outgoing wave that is anything other than you scatter from a point. So the waves out here are all scattered circularly. I'm doing this in 2 dimensions just to be easy. And so I've got a scattered wave that's coming out here. Since the wave phase can only depend upon the distance from the scattering center, it has this e to the I k r on it. K is the same as it was when it came in, because I've stuck my thumb on this nucleus that is at the origin of the coordinate system and not letting it move. And I know that the neutron cannot transfer energy to this nucleus because nuclear energies are so high that this little thermal neutron is just going to tickle it, and it's not going to do anything to the energy inside the nucleus. So the k vector is going to be the same. I also know the inverse square law, and the inverse square law tells me the amplitude of the wave has to vary as 1 over r as I go away from the scattering. So here's a 1 over r. And then this quantity here, minus b, is b is called the scattering length. There is an argument by Fermi in a book that he published about 15 days, I think, before my birth. I won't tell you when that was. In which he argues that the B is generally positive. It has to do with the matching of wave functions of neutrons that are scattered from a nucleus at the boundary of the nucleus. And as you'll see in a minute, most nuclei do have positive values of B. So this is the final scattered wave function, something like this. So now let's try and figure out how many neutrons are going through this area delta S that we had on this previous view graph per second. Well, it's the density of neutrons inside, per unit volume, and that's given by just squaring the wave function, times the volume, and the volume is just the area times how long the volume is that's going to cross that area delta S in 1 second, right? So this is the number of neutrons scattered that are going to cross this area per second. And so you plug this in here and you get this. And ds over r squared is just a solid angle. Now the number of neutrons coming in through some area, that's this thing I had before, is just the square of the incident wave function times the velocity. This, by definition, has an amplitude 1, so this goes to 1. So you have a v here. So now you can write down immediately what the scattering differential scattering cross-section is for a single nucleus, and it's b squared. So think sigma is the integral of this whole thing over omega, and there are 4 pi seradians in a circle. The total scattering is 4 pi b squared, which is within a factor of 2 of the area of the nucleus, right? If I defined it as b over 2, or b over root 2 or something, I'd be fine. So that's where that comes from. Now, I've shoved a bunch of things under the rug, but we'll come back to those in a minute. But that's basically where it is. This is, I'm not going to go through, it's the same thing, but with slightly different notation. Here's these scattering lengths, which I told you were mostly positive. There are a few which are negative. Titanium, vanadium, manganese are negative, but most of them are positive, as Fermi argued that they should be from this wave function matching criterion. And you can also see that they're all about the same, right? There's not, these are scattering lengths in 10 to the minus 12 centimeters. They all vary between about 0.2 and 1. So they are not hugely different. Okay, let's do the same thing for X-rays. So if we want to do this for X-rays, we have an X-ray beam is an electromagnetic wave. So it has an electric field in it, which oscillates. And the oscillating electric field is just this incident field times with some amplitude. And here's the wave bit. It's e to the I k dot r. And then we're going to put the time dependence in here for a reason you'll see in a minute. So this is the incident wave. So what is the scattered wave? Well, the scattered wave is clearly proportional to the amount of charge that's oscillating. So it's an electron, so let's put that in there. Clearly, we're going to have to do the same thing as we did before, the inverse square law. So there has to be an R in here. And then it's going to be proportional to the acceleration of the electron. But if I'm going to observe it at some position r in time t, then it's the acceleration of the electron at the time it was emitting, not at the time that I observe it. So that has to be at a time t when I observe it, minus the distance away divided by the velocity of light. So that's my radiated electric field. Now I've got to figure this one out. This is the acceleration. So it's in phase with the incident wave. So here's my I omega t in here. And the time was the distance away divided by c. This cosine factor here is because I'm observing at some angle phi, and the electric field in the scattered wave vector is going to be perpendicular to that direction, so it's going to have some angle phi with respect to this E field in the incident wave, so I've got to put that in. And then this alpha here is actually a fudge factor for how tightly bound the electron is going to be to the atom. All the other factors are just a bunch of factors that make sure you get the dimensions right. Right. I mean, you can do this properly and get the full answer, but you know the basic pieces that have to be in here, and you can, and the 4 pi epsilon naught you probably get anyway, and then you'd have to put a c squared in here to get the dimensions right. So now I can calculate the ratio of the scattered electric field to the incident, just divide these things out, and I get this thing. And this R naught that comes in here is the Thomson scattering length, and it's defined, it's given by this bunch of constants here, which basically comes from here. And you can see it's about 10 to the minus 15 of a meter, or 10 to the minus 13 of a centimeter, which is of the same order of magnitude within at least better than a factor of 10 of the numbers I was getting for neutrons. So if I now want to find out what the differential cross-section is, I do exactly the same as I did for neutrons, only now I've got to write down what the intensity measured at the detector is in terms of the radiated field, and the area of the, because I want intensity, which is energy per unit area, so energy per unit area of the beam is proportional to this, so I've got to multiply it by this, and then divide by the incident intensity, and if you go through that, you'll see that you get this answer, which is very similar to what you got with the neutron thing. With neutron thing, we had b squared, right? Here we have r naught squared times cosine squared phi. And this one here was for a situation in which the plane of polarization, that is to say the direction of oscillation of the E field, was in this equatorial plane, as was the direction of polarization as the scattered beam. If this thing had been up and down, then we wouldn't have had that cosine factor. So in the case where there's a perpendicular polarization, the cosine factor goes to 1. And if you have an unpolarized beam, you get this as an average. So the two are very similar. This is what what it looks like for X-rays as a function of some angular frequency, which is related to a resonant frequency. Down here in this region, you have a Rayleigh region. That's the scattering by objects that are large compared to the wavelengths. That's why you see the sky is blue. Here's a resonant peak, which it comes from this thing, which, as I told you, had to do with how tightly the electrons are bound. And then you go down to this free electron Thomson scattering length, R0, when you get out to the end here. So that's how it works for both X-rays and neutrons. You can see they're really very similar in approach and in the final form. If we X-rays ask, so neutrons are scattered magnetically. There's a magnetic scattering length, B magnetic, that you can associate with magnetic ions. Electrons are also scattered magnetically because there is an H field associated with the incident electromagnetic wave, but that turns out to be down by about a factor of 10 to the fourth on the scattering due to the electric field oscillating the charge. Nevertheless, it can be seen, especially if you're close to these resonant positions like this. All right, so now what we've got to do, that was just for a single electron in the case of electrons, in the case of X-ray scattering, and a single nucleus in the case of neutron scattering. Now we've got to add this stuff up. Right? We've got to add it up for all of the neutrons all of the nuclei or electrons, depending on whether we're talking about neutron scattering or X-ray scattering, inside a material. And so suppose we have, let's do it for neutron scattering since it's easier to concretize. Supposing you have two nuclei that are separated by some distance r here, and you have a plane wave of neutrons coming in here, and then a plane wave that's scattered out here, you can see that there's a path length difference between the scattering from this nucleus and the scattering from that nucleus. And so there's a phase difference across here when you make the measurement. So basically all you have to do is to add all the amplitudes up with their phase, because I'm postulating that this is coherent scattering for a moment, so the phase matters. And then the total wave function of the scattered beam is just this b that I had before, divided by this. This r, little r here, is the distance from the sample to the detector, and big Ri is the position of the ith nucleus inside the detector. And then I have this phase factor here, which comes from here, right? It's the difference in phase between these two. And I've got to add those up and multiply by the amplitude of the incident wave. So this thing you can write down by inspection. You don't need any fancy calculation. You just write it down by inspection. So that's the total scattering that you get that is elastic and coherent. All right? The magnitude of this wave vector is the same as the magnitude of this wave vector. So now you go through your argument for the differential cross-section, and from the definition we had earlier, you do that and you get this answer. Very simple answer. In other words, this differential cross-section is the sum over all of the nuclei in the system, I and J, of the scattering length of the ith nucleus times the jth nucleus times this phase factor. And it's this phase factor which depends upon the distance between the ith and the jth nucleus that allows you to study the structure of the material. Because the answer is obviously the answer, which is this is what you measure, right? Remember, that's neutrons scattered per second into a little element of solid angle divided by the incident flux. That's what you measure in an experiment, is equal to this. And the same thing for the X-rays. If we go through the X-ray argument, you get this R0 squared, the Thomson scattering length, and you get this factor which had to do with the polarization. I think I called this psi before, but it's the same thing. I've shoved things under the rug. The one big thing I've shoved under the rug is that the atoms don't move, and that comes back to your question, whether it's elastic or not. If the atoms don't move, then for sure it's elastic. But in reality, what happens is the atoms do move, and so I have to take that into account. What I really ought to write here is for this Ri and this Rj, is these ought to be measured at the same time, because it ought to be elastic, right? There ought not to be any movement between while the neutron is or a X-ray is interacting. Okay, so we've had this before, so let's not deal with that. So now let's think about these scattering lengths, the BIs and the BJs. These scattering lengths depend for neutrons on a number of things. They depend upon the isotope. For example, deuterium and hydrogen have different scattering lengths. They're isotopes of hydrogen. Excuse me. They also depend upon the spin state of the nucleus that's doing the scattering. But the spin state of the nucleus that's doing the scattering is not something you know. You only know a statistical for most, unless the spin is 0 of a nucleus. If it has a finite spin, then there are various quantum states that can be occupied that have the same total spin. And each one of those quantum states will have different value of B associated with it. So in fact, this BI here is some average value plus some fluctuation which depends upon which site you look at. By which I mean, the site might be a different isotope, or it might be a different nuclear spin state. So what we have to do is to go through and work out this term here, and you can see if you just plug this definition into here, you get this thing. The average of this delta B is 0 by definition, because this is the average of the BIs. And this thing vanishes unless I equals J. In other words, there's no correlation between the position of, if you have ice which is made of H2O plus D2O, there's no correlation between the position of H and the position of D. And so there's no correlation between the spin states in that case, the isotope states. And the same is true of the spin states. So if you then take that into account, what you find is you get two pieces of this scattering cross-section. There's this piece, which looks exactly the same as the thing you had before, except that now it's got this average B that we're talking about. This incidentally assumes that you've got all the same type of atom. That is to say, it's all, let's say, nickel or all iron or something. But it's easy to change to having different atoms. So we just won't bother with it. And then there's this other part which is incoherent, which has no information about the positions of the atoms. The Ri and Rj don't appear in here. So this is scattering that goes into 4 pi. It's called incoherent scattering. It's uniform in all directions. And coherent scattering, it depends, the magnitude of the scattering depends upon the position of the atoms. So that's the difference between coherent and incoherent scattering. I'm not going to go through the spin state argument. You can do that for yourself if you care. Oh, we've got to stop? Okay. Let me just do this view graph and we'll go. Okay, so this is you can see different values of coherent and incoherent scattering. Here you can see, for example, that the coherent scattering of deuterium is much stronger than for hydrogen, but the incoherent scattering from hydrogen dominates everything else on the chart. You can see, for example, that argon-36 has a whopping great coherent scattering and no incoherent. So this varies for different materials. Aluminum has very low coherent and no incoherent. It's a great material for containing samples, which is why all the cryostat tails that you see in sample environments for neutrons are made of aluminum. That's probably about all I want to say about that. Okay, so any urgent questions? And if not, you guys have to go get your bus. All right, have fun. Oh, yeah. Say it again. Is there no? So this is a very good material for making cans for powder samples, because the scattering is mostly incoherent, so it goes into different directions. And the scattering, due to the structure of the vanadium can, hardly contributes at all because the coherent scattering is very small, right? So if you have a container for a sample that you're going to do diffraction on, you don't want diffraction peaks from the can interfering with diffraction peaks from your sample. And so in this case, the diffraction peaks from your can will be very weak because the coherent scattering is very weak. And this incoherent scattering will be the same in all directions. So it's just a background. So that's the reason. All right, have fun. See you tomorrow.